All right, today we're diving into a physics puzzle that I think is really cool. It seems super simple at first, but trust me, there's a fantastic little twist. So let's get ready to crack the case of the accelerating ramp. So, what's the big mystery here? You put a block on a ramp and gravity wants to slide it right down. Simple enough, right? But what if the entire ramp is moving? How in the world does the block stay put? What's holding it there? That's exactly what we're going to figure out.
Okay, so let's get into the specifics. It's a simple setup. A block, a ramp, a mysterious force. But it's that one little detail about how the ramp is moving that's the game changer.
All right, here are the facts of the case. We've got a block, just sitting on a ramp. The ramp's tilted at a 30-degree angle. Now you'd expect the block to slide, but it's not. It's totally fixed in place, relative to the ramp anyway. And here's the kicker. The whole setup, the ramp and the block together, is accelerating sideways, horizontally. So our job, our mission, is to figure out what's going on with the forces to make all this happen.
Okay, to crack this case, we're going to need a couple of essential tools from our physics toolkit. Think of them as our magnifying glass and our fingerprint kit. They're fundamental concepts that'll let us break this whole thing down.
First things first, we need to decide where we're standing to watch this happen. In physics, we call this our frame of reference, and we're going to pick an inertial one. All that means is we're watching from the sidelines, in the lab, where nothing is accelerating. Why bother? Well, because all the classic laws of physics, the ones we rely on, they work perfectly from this stable point of view. It just keeps the math from getting messy.
And now for the big one, the master key that unlocks pretty much all of classical mechanics, Newton's second law. You've probably heard it, F equals ma. It just means that if you add up all the forces pushing and pulling on our block, gravity, the ramp itself, that total force has to equal the block's mass times its acceleration. This simple, powerful idea is going to be the key to solving this whole puzzle.
All right, toolkit's open. It's time to get to work. We're going to take what we see, this block on a moving ramp, and translate it into the language of physics. We're about to build our one single master equation that describes everything. Okay, I know this looks like a lot of math, but don't worry. Just focus on that main equation at the top. It's really just Newton's second law in disguise. On the left side, you've got all the forces. There's the normal force, which is just the ramp pushing up on the block, and then you've got gravity, mg, pulling it down. And what does it all equal? The right side of the equation, the block's mass, m, times its sideways acceleration, ax. See? Force is in, motion out. Now you might be thinking, why are we tilting our view? It seems kind of weird, right? But here's a pro tip from physics. Instead of sticking to a boring old horizontal and vertical grid, we're going to tilt our whole coordinate system to line up with the ramp. We'll look at forces along the ramp and perpendicular to the ramp. Trust me, this little trick is going to make the math so much cleaner. And bam! Here's our first big clue. By just looking at the forces that are parallel to the slope, what we call the tangential direction, we can suddenly isolate one of our unknowns. See how the math plays out? This lets us solve for ax, the horizontal acceleration of the whole system. That's one mystery down.
Okay, so we've got the acceleration. What's next? We just rotate our view 90 degrees and look at the forces that are perpendicular to the ramp, in the normal direction. And just like that, doing this lets us zero in on our second unknown, N, the contact force. That's the force of the ramp pushing back on the block. And with that, we have everything we need to solve this then.
Okay, the detective work is done. We've gathered the clues, we've built our equations. Now for the exciting part. Let's put it all together and see what we found.
And look at that. After all that work, we get this incredibly clean and simple formula. The contact force in our case, which we're calling F sub 1, is just the weight of the block, mg, divided by the cosine of the angle. It's so neat, but what does this actually mean? To really get it, we need to see how it stacks up against the classic textbook version.
This is the moment of truth. How does the force we just found compare to the one you'd get if the ramp was just sitting there? The one from your high school physics class. Let's put them head to head. This is where we'll see just how much that acceleration really matters.
And here we go, a side-by-side comparison. On the left, our accelerating ramp, F1, where we divide by the cosine. On the right, the stationary ramp, F2, where you multiply by the cosine. Look at that. The only thing that's different is division versus multiplication. But wow, what a difference that makes.
So, how much bigger is our force? The best way to find out is to take a ratio. We'll just divide our force F1 by the standard one, F2.
The cool thing about doing this is that a bunch of stuff, like the mass and gravity, just cancels out. We're left with something that depends only on the angle. Super elegant.
All right, here we go, the grand finale. We take our angle, 30 degrees, and we plug it into that ratio formula we just found. A little bit of calculation, and the number we get is
4/3. That's it. It's not some crazy decimal, just a simple, beautiful fraction. And that fraction tells the whole story.
So what in the world does 4/3 actually tell us? It means the force pushing the block into the ramp is 1 1/3 times stronger than it would be if the ramp was stationary. Or to put it another way, that sideways acceleration is actually increasing the contact force by about 33%. A huge difference. And with that, case closed.
And isn't that cool? It just shows you how even a situation that looks totally basic can have some really interesting physics hiding inside. It kind of makes you look at the world a little differently, doesn't it? If a simple block on a ramp is this surprising, imagine what other puzzles are out there just hiding in plain sight. Thanks for joining me on this one.